Postgres, Redis, or LLM. There are three engines for semantic image search. Same data on the same machine. Bad news first. I don't have a recommendation for you. Good news. What's coming is Ruby code, latency and cost, like always, and a recipe to put a number on carbon. Short enough to fit in one slide. Hi, I'm Michele. I run a small software house near Padua, almost 20 years writing Ruby. I'm a father, I'm an entrepreneur. I ride motorcycle whenever I can, and yes, I love having barbecue on weekends. I'm not an environmental activist, and I'm a regular engineer who started asking himself in his daily job, how much carbon does this piece of code cost me? So let's back to the topic. Postgres, Redis, or LLM? If you ask an engineer in this room, you already know the answer. The answer is, it depends. It always depends. And yeah, that's the joke we made about ourselves. But seriously, depend on what exactly? On the things that you'll already care about. The speed, the cost, the complexity, the quality, and one more, the carbon footprint. We don't usually put this in the table. We can. So first, what semantic search? We have a problem. We got thousands of images, product shots, travel photos, whatever, you name it. And a user types a sentence. Not a tag, not a file name, a sentence. The system has to return the images that means what the sentence means. That's the semantic search. To do it, you need to put you need a way to put text and pixel into the same conversation. Here's the trick: embeddings. We turn every image and every query into a list of numbers. 768 numbers in our case. It's just an array of floats. Items that mean similar things end up with similar arrays, close together if you try to plot them out. We cannot actually visualize 768 dimension, even the engineer can. So this two-dimensional drawing is a metaphor, and so is distance. What we really measure is the similarity score, not meter. The model that produces this array is SeeGlib2. It's a vision language encoder from Google, released in 2025. Its job is to take a piece of text or an image and convert it into an array in the same space. Same dimensionality, same shape. That's what makes it possible to ask a sentence to find a photo. They both end up in comparable arrays. Finding the most similar item in 768 dimension exactly doesn't scale. The naive approach is to compare the query against every single item. Sure, it works for 100 items, but breaks for a million. So we have to approximate. Engineer got nuts with this. The technical name is approximate nearest neighbor, ANN, but don't let the geometric vocabulary fools you. Neighbor here means semantically similar, not physically nearer. The algorithm for both pgvector and Redis is HNSW, hierarchical, navigable, small word. So that part is the same for both solutions. Here we are, 3 engines to solve the same problem. Before any of the 3 engines runs a single query, every image goes through 2 AI models. The first one, SeeGlib2, you have already met. It produces 768 dimension embeddings. The second model is Qwen 3.5, 9 billions, is a multimodal model from Alibaba, released last February. It's pretty new. It can handle text, images, and video natively. We use it to look into the image and write a caption plus a list of tags. The result of both is in one shared file, the manifest.json. So we have the same JSON file for all three engines. We have the same starting point. What's inside? Here is what one manifest record looked like. There are two namespaces, one for the embedder, the geometric solution, and one for the multimodal LLM, for the reasoning solution. The same file, three downstream paths. Okay, keep in mind this slide for the rest of the talk. There are three phases. Preparation, every image gets analyzed once. Siglib2 turns into vector, and Quen write a caption plus tags. Done. Second phase, load. That pre-computed data get pushed into each engine. pgvector loads it once into the database. Stop. Redis load it on every restart because it's an in-memory solution. And the LLM engine never load anything. It reads the file directory every query you push it. The query time. The user type something, the engine answer. Query is the one we'll talk about most, only because it repeats. Every user request pays again and again and again. But preparation and load are real costs, and ignoring them would be misleading. So we kept track of all of these. Last thing. One thing that often gets glossed over, when a user type a sentence, the engine never see that sentence. Siglib2, the same model we use for the images, turn the text into arrays of number embeddings. The same kind of array we computed for every image. That's what reach Postgres and Redis, a list of number. The engine doesn't know English. It only does math on arrays. So let's dive in. Free solution. Two of them are running in production right now, for a fashion client, for a travel photography platform. The third is an internal experiment we built at SeeSaw because we want to see what an LLM-only approach would look like. We didn't build three toys to prove a point. We measure what we already had and added one more dimension to the mix. So the first one, pgvector. The philosophy here is having a durable relational database. You take Postgres, you already have probably, install one extension, and you get a vector column of H, S, and W type. Your DBA doesn't quit, important point, and this is the version running for the fashion client. So here's the search. The query has already become an array. We saw it a few slides ago. Then this SQL cosine similarity via the spaceship operator, then order, then limit. Postgres walk in to the HNSW index and return the top K item most relevant. We have zero Ruby code for the ranking. We delegate everything to the database. The score here is the similarity number. It's the cosine of the angle between two embeddings. And that's all the engines know. It doesn't know why two items are similar. It just computes the math. Semantic search happened earlier when the Siglib produces those embeddings. The search itself is pure vector map. The second one, Redis, HNSW. Here the philosophy is to have all in memory in one process. The same algorithmic family as pgvector. So we have HNSW and cosine distance. But the data is 100% in memory. We can expect sub-millisecond search results. This is the version that is running for a travel photography platform that does live discovery. How it works? Same idea, but on different surface. The ROKN field param syntax complex is a Redis primitive command that does the key nearest neighbor query, KNN. We pack all the embedding in little endians, float 32, because Redis wants binary, doesn't handle strings. And Redis returns us the key nearest in a single shot. is volatile by design. So if we lose the process, we lose the index. We have to reload it. It's not a problem because we had a manifest.json saved on disk. The third one is structurally different. We have no index, we have no load phase. We feed all the candidates to the Qwen 3.5 9 billion that is run locally on LM Studio. And the same Qwen model we use to write the caption and the tags. It's multimodal, so it can handle images, but at runtimes, we only pass it the caption and the tags, not the pixel. All the 200 images of the test batch, every single query. The big O notation of this algorithm is ODN. It's not sublinear, it's linear. Let me say it plainly. This is a baseline, it's not a production design. At any real scale, you would put a retrieval in front of it. We keep it pure on purpose because the point here is the trade-off. How it works? Strict JSON in, caption and tags, scores out. No pixel at search time. Take a look at the DAX section. Each slice of batch size, because the catalog doesn't fit entirely in one prompt. So we have to do batch of candidates. Then sort each batch result globally. The final sort is the re-rank, and it merges separate candidates into a single ordered list. The result we want. Temperature of the LLM here is 0. So we have the same query, almost the same answer at every run. The pattern here isn't tied only to LLM scores. Everything you can score here, you can use. You can re-rank for tags, full text search, selling department priority, whenever you want. This approach generalizes. Quick detour, because someone in this room is already thinking about it. Nobody runs a 9 billion parameter model over the whole catalog in production. You're right. Nobody does. The standard pattern is this one. Retrieve, then re-rank. A fast vector search, stage 1, pgvector, Redis, whatever you want, pulls a small number of candidates, 50, for example, in milliseconds, and then LLM re-ranks only those with reasoning. Same word as before, but in different scope. In our pure engine, the re-rank merge each batches. In the production pattern, the re-rank reorder only the survivor of a first stage. Same operation in code, different role in the architecture. So, you might ask why I build it that way. Because we want to see what is the reasoning cost in isolation. If I put a retrieval stage in front of our solution, the 95% of the work is geometric search, and the LLM energy gets drawn out by the noise. So keep it pure is how we measure it. The number you see in a couple of minutes are and not a recommendation from us, are the price tag on a component you can compose. So, take solution, different word inside, same shape outside. pgvector, open a Postgres connection, run the SQL with HNSW. Redis, open a Redis connection and run KNN query in one shot. The LLM loads the whole manifest, build candidate, call the re-ranker. These are three radically different operations. SQL similarity, search, in-memory KNN, and batched LLM scoring. But every one of them returns the same return to the same caller, build search result with the same field and the same column names. So from the calling code, they're interchangeable. You pick an engine today, you pick another tomorrow, and the rest of the system doesn't even notice. The architecture here decouples the choice from the consumer. The numbers. But before the numbers, the methodology. How we put number on these engines. Free architecture, the same output contract. So how do we pick? We have 5 axes: speed, cost, complexity, quality, and carbon footprint. 4 of these have a shared vocabulary in the daily engineering conversation we had. The 5th one doesn't yet. The next slides are about that. What serious people do, what we do, and the honest gap between the two. The whole thing fits in one slide, I promise. So here's what rigorous looks like. The European standard for cloud carbon computing is a public, well-defined standard. Real cloud provider have to implement it. There are 5 formulas with multiple terms. I do the math for you. 21 data points minimum from manufacturers, data center sensors, grid operator, and many other. We have access to none of them, so we won't try. Instead, a software carbon intensity light is a spec from the Green Software Foundation, is a public standard for calculating the carbon impact of running software. Anyone can read it, anyone can implement it. We use a simplified version with only the operational part. The full SCI standard asks you to amortize the embodied emission. What is it? Is the carbon cost of manufacturing your hardware, but requires manufacturer data that we don't have. So we drop it on purpose, and what we'll use? Absolute precision. What we gain? A decision grade comparison that anyone can reproduce. So drum rolls. Here's the recipe. Here it is, the whole thing. What times second times grid intensity. As I told you, it fit in one slide. What time second gives joules. Joules time grid carbon intensity give you grams of CO2 equivalent. We apply it to each phase: preparation, load, and query. The Italian grid average for 2025 is 215.9 grams per kilowatt hour. Is declared by the Italian government. We cannot tell you the absolute cost of a query, but we can tell you which solution costs significantly more than the other. So, how we measure? No jams, no estimating tool, 10 lines of Ruby. The monotonic clock measure duration correctly because time.now can sometimes jump backward. And in the dark part, the same idea wrapped into the energy probe. There are 3 levels of graceful degradation. Probes work, we get energy plus time. Probe return nothing, we get time only. Probe explodes, we still get time. The whole benchmarking infrastructure is on the screen. The setup, we rent a Mac Mini Pro M4 with 32 gigabyte, hosted, bare metal, no virtualization, no shared core. The power probe is power metrics tool from Apple. We sample 5 times per second the cheap power model of the Mac Mini. It's not a wall socket measure, but it's consistent across runs. Both the LLM models run natively. Siglib2 through an MLX adapter, Quen on LM Studio at temperature 0.0 is reproducible by anyone with a Mac in a weekend. So, 4 honest disclosure. The first one, power metrics are estimation and not measurement at wall socket. The neural engine sometimes report 0 milliwatt under load. It's a feature Apple gave us. We don't include training emission for either model, not because they cancel out, they don't, but because they are not published and are not auditable. Every model run through some types of runtime, Docker, LLM Studio, LM Studio, I'm sorry, Python. Each one adds a few percentage points of overhead. Show me the number. Headline metrics. Gram of CO2. Oh no. These are per query. On the same machine, the same dataset, the same protocol. The bar on the left are in absolute, but I'll rather you read the panel on the right is the ratio. Because what travel across the hardware, across the grids, across the country is the ratio, not the grams. Your mileage will literally vary. The shape of the bar is the message. Before we go on, let's complete the picture. Prepare, load are real cost. Prepare is shared. Every engine starts from the same manifest, so this column appears 3 times. Load is where pgvector and Redis pay something that LLM doesn't pay, because it doesn't load anything. Query is where everyone pays every time. None of this changes the conclusion of the previous slide, but is not misleading anymore. They are real cost. The speed, so the latency, axis number 2. The geometric resolution are under millisecond range, no surprise. The LLM lives on a different scale because it has to read the catalog, the whole catalog every time. With 200 images in batches of 40, we are looking at 5 sequential calls to the 9 billion parameter model. There's no clever indexing that gets you out of that. It's the price of reasoning at runtime. Let's come to the cost. The same shape as latency chart you just saw. It's the same. And that's the whole story. Because hourly rate is fixed. We rent our Mac Mini by hour. It's fixed cost. The cost per query is linear and is linear in the time you spend on it. Fourth axis, quality. This is the messiest axis, and we don't pretend otherwise. The same query, top result from each engine. The similarity-based solution optimizes a math objective, cosine similarity. And you can see it. Note the by hand in the query. Results are tightly related to the query, but sometimes it's literally related to the query. For the first 2 engines, it's the case. The LLM results is more contextual, is more aware of the intent, and occasionally just wrong, because it is reasoning on caption and tags, not on the pixel. There's no winning here. There's no winner here. Sorry. It's fit for purpose. The last one, adoption complexity. It's not a number, it's a traffic light, because if you have Postgres, you can ship pgvector in an afternoon. If you choose Redis, HNSW, you need version 8, binary vector handling, but come on, it's Redis. The red one, an LLM running locally drags you into a completely different ecosystem entirely. You need a model server, a prompt to maintain, hardware that truly makes the difference, and that's pretty much it. None of these are wrong. They simply are not on the same shelf. 5 axes, 3 engine, 1 shaper engine. Read the polygon first. Each engine has a distinct silhouette, and that's the punchline. There's no ideal triangle here. Each shape tells you what the engine is optimized for and what costs you elsewhere. There's no single winner, depending on your case. But we have we have one column here we didn't have before, and you can compute it on a Mac Mini in a weekend. So I'm almost done. Quick recap of what we did, and then I'll let you go. Postgres, Redis, or LLM? It depends. The same answer of 24 minutes ago. But now depend on 5 axes, not on 4. The numbers themselves are mine, of course, on my dataset, on my hardware, but the method travels. So why I'm bothering you? Because every query you ship pays a cost in carbon, like it pays a cost in latency and pays a cost in euro. We already have a shared vocabulary for the last two, but we don't have yet for the carbon one. I believe we should start considering the cost that we usually don't. And this is the only thing I want to leave you with. I'm not changing the world with a Mac Mini and Powermatics, and neither are you. But I'm starting to think about it in my daily job and when I pick a tool. That's the part that for me is worth something. It's not a manifesto. It's just a number alongside the other you already weigh. Thank you.